Some galaxies are spinning backwards, and it breaks our understanding of the universe. For decades, this cosmic puzzle has challenged our most fundamental laws of physics. You will learn why these galactic anomalies exist and what they reveal about the hidden forces shaping our cosmos. We will explore ancient galaxies with warped disks and investigate whether dark matter or cosmic collisions hold the key. What does it mean for our reality when the universe itself seems to defy its own rules? Our universe should run like a perfect cosmic clock. Galaxies spin in a grand, predictable ballet governed by gravity's unbreakable rules. This elegant motion begins with the birth of the galaxies themselves. Picture an immense, slowly drifting cloud of gas and dust in the early universe. As its own gravity pulls it inward, it begins to collapse, and just like a figure skater pulling their arms in to spin faster, this vast cloud spins up as it shrinks. This is a fundamental rule called the conservation of angular momentum. It means the total amount of spin in a system must remain constant. Once that rotation begins, it is locked in, defining the galaxy's spin for billions of years. This initial spin is not random. It is shaped by the tug of neighboring matter and the subtle twists imprinted by the universe's large-scale structure, a cosmic web of dark matter that acts as an invisible skeleton. This mysterious substance provides the extra gravity needed to hold fast-spinning galaxies together, preventing them from flying apart. Think of a well-made spinning top. Once set in motion, it rotates smoothly and stably on its axis. That is exactly how we expect spiral galaxies to behave. This predictable clockwork is the foundation of modern astronomy. It allows us to rewind the cosmic tape, to model how structures formed, and to trace the history of the universe itself. So when we point our telescopes at the sky, we expect to see order. We expect to see the rules obeyed, but the cosmos has a way of surprising us. What do you do when you look up and see a top spinning the wrong way? The first crack in this cosmic clockwork appeared not with a dramatic shatter, but with a quiet, persistent whisper of data. In the mid-1950s, as astronomers trained new, more powerful telescopes on the heavens, they began noticing something deeply unsettling about certain spiral galaxies. While most spun in a way that seemed harmonious with their place in the cosmos, a few displayed a rotation that was completely backwards. They called it retrograde rotation. This discovery was made possible by a clever technique using the Doppler shift of starlight. Just as a siren's pitch drops as the ambulance races away from you, the light from stars shifts in color. Stars moving toward us glow a slightly bluer hue, while stars speeding away from us shift toward red. By meticulously mapping these red and blue shifts across a galactic disk, astronomers could chart its spin. The expectation was a clean, symmetrical pattern confirming an orderly rotation. But for some galaxies, the map was inverted, the colors swapped. It was as if the entire galactic disk was spinning in reverse. The initial reaction among many scientists was pure disbelief. They assumed it was an optical illusion, a trick of the telescope's lens, or an error in their photographic plates. How could a galaxy possibly spin the wrong way? The technology of the era was a major hurdle. Early observations were grainy and faint, making it easy to dismiss a single anomalous reading. For decades, the debate simmered in the background of astronomy. Skeptical papers argued the anomalies were mere artifacts, while a handful of excited researchers pointed to them as clues to a deeper truth. Studies of satellite galaxies around our neighbor, Andromeda, began revealing these peculiar rotational behaviors on a smaller scale, adding more fuel to the quiet controversy. Why did it take so long for the scientific community to take these backward-spinning galaxies seriously? The tools to see them clearly, to prove their existence beyond a shadow of a doubt, simply did not exist yet. The true scale of the mystery was waiting for a new generation of eyes to look upon the cosmos. The true breakthrough in this cosmic detective story arrived not with a new theory, but with a new way of seeing. Astronomers developed a brilliant method to listen to the music of the galaxies. They learned to read the subtle color changes in starlight, a phenomenon known as the Doppler shift. You experience this every time an ambulance speeds past you. Its siren sounds higher pitched as it races toward you, and then the pitch drops dramatically as it moves away. Light behaves in a nearly identical way. When a star in a distant galaxy moves toward us, its light is compressed, shifting it slightly toward the blue end of the spectrum. When a star moves away, its light is stretched, making it redder. By pointing a powerful telescope equipped with a spectrograph at a galaxy, scientists could map these tiny blue and red shifts across its entire disk. This process is like turning the galaxy into a giant spinning vinyl record. We cannot hear its rotation, but we can see the equivalent of a rising and falling pitch from its stars, allowing us to chart its precise spin. Early spectrographs used simple prisms to split light into its constituent colors, revealing the faint fingerprints of these shifts, but the data was often blurry and open to interpretation. The revolution came with instruments like the Hubble Space Telescope, which floated above the distorting blanket of our atmosphere, and massive ground-based observatories with mirrors polished to near perfection. These technological marvels could collect starlight with incredible precision, splitting it into a rainbow so detailed that the Doppler shifts became unmistakable. Astronomers were initially supremely confident. They expected to point these powerful tools at any spiral galaxy and see a clean, beautiful rotation curve, a perfect confirmation of the cosmic clockwork. And for many galaxies, that is exactly what they found. But when they turned their gaze to the anomalous ones, the data told a different story entirely. The map of red and blue shifts was completely reversed. It was the ultimate confirmation that these galaxies were genuinely spinning backwards, yet these advanced tools revealed something even stranger. They showed that some galactic disks were not flat but warped like a potato chip. Others had central cores that were misaligned with the outer arms, as if the galaxy's heart was spinning on a different axis from its body. The very instruments designed to provide answers had instead ripped open a deeper layer of mystery. The universe was not just breaking the rules, it was doing so with a bizarre and flamboyant complexity that no one had predicted. That hidden hand guiding the stars has a name: dark matter. This invisible substance is the universe's greatest unsolved mystery, a ghostly presence that binds galaxies together. The entire concept of dark matter was born from a puzzle very similar to the one we face now. In the 1970s, astronomer Vera Rubin was studying the rotation of spiral galaxies when she made a startling discovery. According to the laws of gravity, stars on the outer edges of a galaxy should orbit much more slowly than those near the bright center, just as Pluto takes far longer to orbit the Sun than Mercury does. But Rubin's data showed something completely different. The outer stars were racing around just as fast as the inner ones. It was as if the entire galaxy was spinning like a solid plate, a rigid vinyl record. This was impossible according to the gravity from the visible stars and gas alone. The only logical explanation was that a vast, invisible halo of something was enveloping each galaxy, providing extra gravitational glue to hold these fast-moving stars in place. That something is what we now call dark matter. Think of it as the invisible scaffolding of the cosmos, an immense spherical cloud that cradles every galaxy. We cannot see it, touch it, or interact with it through light, but we can feel its gravitational pull. This standard model, the dark matter halo, became a cornerstone of modern cosmology. It elegantly solved the mystery of those unexpectedly fast rotation speeds. As one prominent cosmologist put it, dark matter is the hidden architect that dictates the motion of everything we see. But here is where our story takes another strange turn. While dark matter beautifully explains why galaxies spin so quickly, it does not naturally explain why some of them would spin backwards. The gravitational pull from a spherical dark matter halo should be uniform, gently guiding a galaxy to spin in the direction it first started. It should not, by itself, cause a galaxy to reverse its rotation. So if this unseen cosmic architect is responsible for the speed, who or what is flipping the direction? This glaring discrepancy hints that our models, as successful as they are, might be incomplete. Perhaps dark matter is not as simple as a smooth, spherical cloud. Maybe it can be stirred or clumped or shaped by forces we do not yet understand. The mystery of the backward-spinning galaxies suggests that the invisible hand guiding our universe might be more complex and more surprising than we ever imagined. The strangeness does not end with entire galaxies spinning backwards. A deeper, more intricate puzzle emerged when astronomers discovered galaxies where different parts of the system were spinning in direct opposition to one another. Imagine a vast river where the water on one side flows peacefully downstream, while a powerful, hidden current on the other side surges relentlessly upstream. This is the chaotic reality inside galaxies like the famous NGC 4550. Detailed kinematic maps, which act like cosmic motion trackers, revealed that nearly half of the stars in this galaxy orbit in one direction, while the other half orbit in reverse. These two populations of stars are intermingled, sharing the same space but moving in a breathtaking celestial counterpoint. For scientists, this was like discovering a machine with gears turning perfectly in opposite directions, a configuration that should, in theory, tear itself apart. How could such a complex and seemingly unstable system form from a single, collapsing cloud of gas? The initial, elegant model of a galaxy spinning up like a figure skater completely fails to explain this internal civil war. The most logical suspect is a galactic merger. Picture a smaller galaxy, perhaps a dwarf, being captured and consumed by a larger spiral. If the smaller galaxy approaches from a certain angle, its opposite spin could be imparted to a new generation of stars, creating this dual-stream dynamic within the larger galaxy. It is a compelling story, one of cosmic violence and assimilation. Yet, the evidence is not always there. Many of these counter-rotating galaxies show no visible scars, no distorted tails of stars, or other telltale signs of a recent collision. They appear serene and intact, as if they were simply born with this built-in contradiction. This forces us to ask a more profound question. Could these opposing currents be the result of something more subtle than a dramatic crash? Perhaps vast rivers of gas, flowing in from the cosmic web over billions of years, could have arrived with their own inherent spin, slowly seeding the galaxy with a new, opposing rotation. Or maybe the dark matter halo itself, that invisible scaffold, possesses a complex spin that can, under the right conditions, imprint these bizarre dynamics onto the visible galaxy. The very existence of these divided galaxies suggests that the story of galactic formation is far from a simple tale of birth and steady growth. It is a history written in collisions, accretions, and influences we are only beginning to trace. This galactic civil war, with stars moving in opposite directions, points toward a dramatic and violent origin story. the most compelling suspect in this cosmic mystery is a galactic merger. Picture two immense star cities, each containing hundreds of billions of suns, slowly drifting toward one another over cosmic time. Their initial approach is not a head-on collision, but a gravitational dance, a slow, graceful spiral that can last for billions of years. As they draw closer, their mutual gravity begins to warp their shapes, stretching them into long, streaming tails of stars and gas. These are the tidal forces, the same kind of pull our moon exerts on Earth's oceans, but operating on an unimaginable scale. During this chaotic pass-to-due, the angular momentum of each galaxy, the direction and strength of its original spin, becomes a key ingredient in the final product. When these two spinning systems combine, their rotational energies do not simply add together. They interact in a complex tug-of-war, often resulting in a new spin direction that is completely unpredictable from the original two. You can witness this process in famous examples like the antennae galaxies, where two spirals are actively colliding. Telescopic images show a spectacular mess of newborn star clusters and tangled dust lanes, a celestial explosion of creation and destruction. The motion within this chaos is anything but orderly. Researchers who create supercomputer simulations of these events, known as N-body simulations, watch as virtual galaxies evolve over billions of years. One scientist who specializes in these digital universes explains that the outcome is highly sensitive to the initial conditions. A slight difference in the angle of approach or the relative size of the two galaxies can produce a final system that spins forward, backward, or even has a wildly tilted axis. The statistics from these models are telling. Galaxies with clear merger histories are far more likely to exhibit these anomalous rotation patterns, including retrograde motion. It is a tempting and elegant solution. Yet, the evidence on the ground, or rather in the sky, is not always so clear-cut. We find galaxies spinning the wrong way that appear completely isolated, serene islands in the cosmic sea with no visible signs of a violent past. There are no distorted tails, no shells of disrupted stars, no companion galaxies nearby that could have been consumed. For these pristine-looking anomalies, the merger explanation feels strained. It is as if a clock were running backwards with no one having ever touched it. This glaring inconsistency pushes the mystery into deeper territory. If a galactic crash is not always the culprit, then what other cosmic mechanism possesses the power to flip a galaxy's spin? The search for an answer forces us to look beyond the violence of collisions and into the subtle, hidden currents of the cosmos itself. Our universe resembles a colossal, three-dimensional spiderweb. Galaxies are not scattered randomly through the void. Instead, they cling to vast, intersecting strands of dark matter, forming an immense structure astronomers call the cosmic web. A galaxy's home within this web, whether nestled in a dense urban cluster or strung along a lonely rural filament, may be the invisible hand that twists its destiny. Within the crowded core of a galaxy cluster, thousands of galaxies swarm together in a relatively small volume of space. Here, the gravitational tides are immense and constant. Picture a leaf caught in a complex network of swirling river currents. It does not simply float downstream. It is constantly nudged, spun, and torqued by the competing pulls of the water around it. In a similar way, a galaxy orbiting through a dense cluster is subjected to a continuous gravitational massage from all its neighbors and from the cluster's overarching dark matter halo. These tidal forces can slowly, over billions of years, torque the galaxy, altering the axis of its spin or even reversing its direction entirely. This is a gradual process of cosmic peer pressure, where the environment itself reshapes the individual. Observations seem to support this idea. Some sky surveys have noted curious correlations, finding a slightly higher number of retrograde rotators in certain cluster environments or along the specific filaments that feed matter into these dense hubs. Cosmologists who simulate the growth of this large-scale structure watch as these cosmic rivers of gas and dark matter flow into the waiting gravitational wells of clusters. One researcher describes it as a galaxy being processed by its environment, its spin becoming a fossil record of its long journey through the cosmic landscape. Yet, for all its compelling logic, the environment alone cannot be the whole story. The predictions from these grand simulations often fall short of the actual number of backward-spinning galaxies we observe. Many galaxies in these supposedly torque-heavy environments spin perfectly normally, while some of the most dramatic retrograde rotators are found in relative isolation, far from the gravitational tumult of clusters. This leaves us with a profound environmental puzzle. It suggests that a galaxy's spin is not merely a product of its birth or its violent mergers, but is also shaped by the subtle, billion-year currents of the cosmic web. But if even this vast, large-scale influence cannot fully account for the backward spinners, then we are forced to question the very laws that govern motion itself. The most stubborn challenge to our understanding spins in the deepest voids of space, far from the gravitational crowds of galaxy clusters, in the cosmic equivalent of an empty desert. Astronomers have found solitary galaxies spinning the wrong way. These isolated retrograde rotators dismantle the most straightforward explanations. If there is no neighboring galaxy to collide with and no dense environment to torque it, what force could possibly reverse its spin? Massive surveys like the Sloan Digital Sky Survey have methodically mapped millions of galaxies, revealing these profound outliers. They are the rule breakers that cannot be explained by a violent past. One of the most striking examples is UGC 7321, an incredibly thin, delicate spiral known as a super-thin galaxy. It floats in an immense and empty region of space, a lone island with no close neighbors for millions of light years. Yet its kinematic data reveals a rotation that is subtly off, a motion that does not fit the clean predictions of our standard models. It is like finding a solitary, perfectly balanced top spinning backwards in the middle of a vast, empty room, with no one there to have ever touched it. As one astronomer who studies these field galaxies admitted, these isolated anomalies are the most perplexing. They offer no visible clues, no scars or nearby suspects to blame for their strange behavior. Their very serenity is what makes them so deeply mysterious. This isolation creates a fundamental problem for scientists. How do you piece together the history of an object that has been alone for billions of years? With no recent interactions, the cause of its backward spin must be ancient, locked into its very formation. Could the answer lie in the primordial conditions of the universe itself? Perhaps a rare, powerful twist in the dark matter web, a knot of invisible substructure, set this galaxy spinning on its unusual path from the very beginning. Or maybe the dark matter halo surrounding it is not a simple sphere, but has a lopsided, rotating core that exerts a strange torque on the visible stars. These are compelling ideas, but they remain frustratingly theoretical. We simply lack the conclusive evidence to confirm them. The silent, backward spin of a galaxy like UGC 7321 is a quiet but undeniable challenge. It forces a humbling admission. Our models of how galaxies are born and live their lives, models built on mergers and environmental influences, are clearly missing a vital ingredient. The cosmos is pointing toward a deeper, more fundamental process we have yet to grasp. Perhaps the solution is not to find more invisible matter, but to rewrite the rules of gravity itself. This radical idea is the heart of a controversial theory known as modified Newtonian dynamics, or MOND. Its central premise is as simple as it is profound. What if our understanding of gravity, a force we thought was settled by Isaac Newton and refined by Albert Einstein, is actually incomplete on the vast scales of galaxies? MOND proposes that gravity does not weaken with distance in the exact way our textbooks say it does. Instead, at extremely low accelerations, the kind found in the faint outskirts of galaxies, gravity gets a subtle boost. It becomes stronger than expected. This single change could potentially explain why stars on the outer edges of galaxies orbit so quickly, all without needing any dark matter at all. Think of it like this: you have been playing a board game your whole life with a strict set of rules, but you keep encountering situations the rules cannot explain. Instead of inventing invisible players to make the game work, MOND suggests we might have been misreading the rulebook all along. The theory was pioneered by physicist Mordechai Milgrom in the early 1980s, directly inspired by the flat rotation curves of galaxies that baffled Vera Rubin. Proponents of MOND argue it is a more elegant solution. It uses the matter we can actually see to explain the motions we observe. In certain galactic configurations, the modified gravitational fields predicted by MOND can even produce effects that mimic retrograde rotation or other anomalous spins, offering a potential pathway to explain some of our cosmic mysteries without invoking dramatic collisions or complex environmental influences. There are striking successes. For a number of individual galaxies, MOND predicts the exact shape of their rotation curves with remarkable precision, something the standard dark matter model often struggles with unless its halos are carefully fine-tuned. Yet for all its intriguing promise, MOND faces its own monumental challenges. It largely fails to explain the gravitational dynamics within massive galaxy clusters, where the need for unseen matter is overwhelming. It also struggles to account for the precise patterns seen in the cosmic microwave background, the afterglow of the Big Bang, which is considered a cornerstone evidence for dark matter. Mainstream cosmologists point out that while MOND might patch one hole in our knowledge, it opens up several others in the wider fabric of cosmology. Most critically for our mystery, MOND does not naturally or consistently explain why some entire galaxies would spin backwards while their neighbors spin forward. The theory can adjust the strength of gravity, but it does not readily provide a mechanism to reverse a galaxy's primordial spin direction on such a grand scale. So we are left at a crossroads. Dark matter provides a powerful framework for the entire universe but cannot easily account for every galactic anomaly. Modified gravity solves some specific galactic puzzles but stumbles when faced with the cosmos as a whole. The stubborn existence of backward-spinning galaxies, especially those in isolation, suggests that neither idea alone may be the final answer. The true solution might lie in a more complex, integrated picture we have not yet conceived. There is another, more subtle force weaving its way through this mystery. Winding through the vast spaces between the stars are immense magnetic fields, threads of invisible energy that stretch across entire galaxies. These fields are incredibly weak, far too faint to be felt by us here on Earth. But over billions of years, their gentle, persistent pull can act like an invisible hand, slowly guiding the flow of cosmic material. The space between stars is not a perfect vacuum. It is filled with a thin, ionized gas, a plasma where electrons have been stripped from their atoms. Because this gas is electrically charged, it becomes captive to the galaxy's magnetic field, locked in a delicate dance between gravity and electromagnetism. The field acts like a network of cosmic rails, and the ionized gas is the train, compelled to follow its path. plasma astrophysicists use a complex field called magnetohydrodynamics to model this interaction, essentially studying how magnetic fields and fluids behave as one. Their simulations reveal that these magnetic fields can exert a torque, a twisting force, on the spinning galactic disk. Over eons, this force can gradually alter a galaxy's rotation, changing its axis or causing its inner core to become misaligned with its outer arms. It is a process of cosmic persuasion, not violent force. Radio telescopes have given us glimpses of this hidden architecture. When we observe certain retrograde rotators with instruments like the Very Large Array, we can map the structure of their magnetic fields by detecting the radio waves emitted by electrons spiraling along the field lines. In some of these anomalous galaxies, astronomers have found surprisingly ordered and powerful magnetic fields, their patterns curiously intertwined with the galaxy's strange spin. This hints at a deep, long-term relationship, yet for all their subtle power, magnetic fields are unlikely to be the sole architect of a backward-spinning galaxy. The force of gravity, whether from visible stars or dark matter, is millions of times stronger on the galactic scale. Think of it as trying to steer a massive supertanker by blowing on its sail with a steady breath. Your breath will have an effect given enough time, but it cannot single-handedly reverse the ship's course against the powerful currents of the ocean. Most astrophysicists agree that magnetic forces are a secondary player, a complicating factor that can nudge and tweak a galaxy's motion, but not completely flip it. Their presence adds a beautiful layer of complexity to the puzzle, suggesting that the final rotation of a galaxy is not dictated by one force alone, but is a symphony conducted by gravity, shaped by collisions, and subtly orchestrated by these invisible magnetic threads. The very fact that we must consider such a delicate and prolonged influence shows just how deeply we are digging into the heart of this cosmic mystery. The elegant flat disk of a spiral galaxy is often an illusion. Many of these cosmic pinwheels, including our own Milky Way, possess a distinct warp, their outer edges bending upward or downward like the brim of a soft hat. These warps are not rare defects but common features, subtle distortions that reveal a galaxy is not a rigid structure but a fluid, dynamic entity. We can detect these bends by observing the cold hydrogen gas that traces a galaxy's outer limits, or by mapping the faint glow of old stars in infrared light, which pierces through the obscuring dust of the galactic plane. Our own galaxy's disk is noticeably warped, its outer rim twisted into a shape reminiscent of a potato chip, a fact we can only discern by looking at the collective motion of billions of distant stars. Another stunning example is NGC 4013, a galaxy seen perfectly on its edge from our vantage point. Its thin disk of starlight curves at the ends into a graceful cosmic integral sign, a silent testament to some unseen force acting upon it. The leading theory points to a misalignment between the visible galactic disk and its invisible dark matter halo. If the disk forms and spins within a halo that is itself tilted or shaped like a squashed beach ball, the gravitational tug of war can slowly torque the disk, forcing its outer regions to bend over billions of years. External forces can also be to blame. A close encounter with a smaller satellite galaxy, or the steady gravitational pull from the cosmic web, can exert a torque that warps the disk. Yet the persistence of these warps is a puzzle in itself. One would expect such a bend to either flatten out over time or to oscillate, wobbling like a spinning plate. As one dynamics researcher notes, the fact that we see so many warped disks suggests they are either being continually driven by an external force, or they are long-lived vibrational modes of the galactic disk itself, a kind of slow, persistent ringing that never fully fades. These warps are not merely a matter of shape. they profoundly complicate our measurements of galactic spin. A severely warped disk, when viewed from a certain angle, can create the illusion of retrograde motion in its outer regions. The stars and gas in the bent section might be following a perfectly normal orbit, but from our distant perspective, their path can appear to reverse direction. This creates a nightmare for astronomers trying to determine if a galaxy is truly spinning the wrong way, or if we are simply being tricked by its twisted geometry. The connection between warped disks and genuine retrograde rotation runs deep. Both anomalies could be different symptoms of the same underlying cosmic disturbances. An accretion event, where a galaxy slurps a stream of cold gas from intergalactic space, could deliver not only fresh material but also a new angular momentum, simultaneously warping the disk and altering its spin. Similarly, an interaction with a clump of dark matter could torque both the halo and the disk within it, linking the visible warp to an invisible cause. The prevalence of these bent galaxies serves as a powerful reminder. Galaxies are not frozen sculptures but living systems, their forms and motions constantly evolving under a symphony of forces, both seen and unseen. Their warps are the subtle, lasting impressions of a dynamic and often violent history. Supercomputers now act as our cosmic time machines, running entire universes in silicon to test our theories. Projects like Illustris and Eagle do not simulate just one galaxy. They build entire virtual cosmos, tracking the birth and life of millions of galaxies across billions of virtual years. These are digital laboratories where we can rewind and replay the history of the universe, tweaking the fundamental rules to see what happens. The process begins with a snapshot of the early universe, a sea of dark matter and primordial gas, and then lets the unbreakable laws of physics play out. The goal is to see if these digital universes, governed by our best models, can spontaneously produce galaxies that look and spin like the ones we see in our own night sky. The challenge is staggering. Simulating a galaxy requires modeling phenomena operating at wildly different scales, from the slow, gravitational pull of a dark matter halo light years across to the violent supernova explosions that tear through a single stellar nursery. Star formation and the resulting feedback, the energy and matter these stars blast back into space, are particularly difficult to capture. Get this balance wrong, and a simulated galaxy will either burn through its fuel too quickly and die or form stars in a burst of unrealistic perfection. Dark matter's behavior, whether it is cold and collisionless or possesses some unknown internal properties, is another critical variable that shapes the final spin of every virtual galaxy. When researchers sift through the vast digital catalogs from these simulations, they do occasionally find retrograde rotators. A virtual galaxy will sometimes spin the wrong way, often as the result of a clear merger event or a complex series of gravitational interactions with its cosmic environment. Yet these backward spinners are almost always rare outliers, statistical oddities in a sea of normally spinning galaxies. The real universe, by contrast, seems to have a more generous quota of these anomalies. This is a telling discrepancy. As one computational astrophysicist noted, the simulations are telling us that our standard recipes for building galaxies naturally produce order. To get the level of chaos we actually observe, we must be missing an ingredient. There are glimpses of success. In certain high-resolution simulations, when the initial conditions are carefully fine-tuned to mimic a specific, violent cosmic history, the code can produce a galaxy with a warped disk or a counter-rotating core that closely matches a real-world counterpart. But this feels less like a prediction and more like a digital reconstruction, a confirmation of a known event rather than a true explanation for the sheer number of isolated rule breakers. The persistent gap between the simulated universe and the real one points toward a profound truth. Our digital cosmos are only as good as the physics we program into them. If we are missing a fundamental process, perhaps a subtle interaction within dark matter or a large-scale magnetic influence we have not yet quantified, then our most powerful simulations will consistently fail to reproduce the full, messy reality of galactic spin. This digital shortfall is not a failure but a brilliant guidepost. It illuminates the path forward, showing us exactly where our understanding of the cosmos remains incomplete. Edwin Hubble gave us a map for the cosmos, a way to bring order to the countless islands of stars. His famous tuning fork diagram sorts galaxies by their shape, from the smooth, football-shaped ellipticals to the majestic spirals with their coiled arms. This classification suggests a simple story that galaxies evolve along a path from one type to another. Spiral galaxies with their prominent disks are defined by their rotation. It is their very essence, yet when we look closer, this neat arrangement begins to unravel. The direction and stability of that spin vary so wildly that it challenges the very categories we have created. Studies that cross-reference galaxy type with kinematic data reveal startling patterns. Lenticular galaxies, the S0 types that sit between spirals and ellipticals, show a surprising propensity for counter-rotation. Many have central bulges of old stars that spin in direct opposition to their outer disks, a clear sign of a complex and layered history. The rotation curves themselves, the graphs that plot orbital speed against distance from the core, tell their own divergent stories. A classic spiral might show that flat curve, the signature of dark matter's hold, but another galaxy of the exact same Hubble type might display a curve that rises unexpectedly or falls away sharply, its motion governed by a different, hidden logic. This is not merely a statistical fluke, it is a fundamental clue. Astronomers analyzing data from massive surveys like Caliphate have found that kinematic diversity is the rule, not the exception. As one researcher noted, we assumed shape was a reliable proxy for a galaxy's internal motion, but we are finding that two galaxies can look like identical twins and spin in completely different ways. This forces a difficult question. Is a galaxy's place on the Hubble sequence a true indicator of its history, or just a snapshot of its current appearance? The growing catalogue of wrong-way spinners makes the problem acute. These rotational anomalies are not confined to one branch of the tuning fork. They appear in grand design spirals, in flocculent spirals, and especially in those transitional S0 systems. Their prevalence in certain types implies that a galaxy's morphology and its spin are deeply connected, but not in the simple way Hubble envisioned. A lenticular galaxy with a counter-rotating core almost certainly formed from a quiet, steady accretion of external gas, a gentle cosmic rain that fell with an opposite spin. A warped spiral spinning backwards, however, points to a more violent interaction. The taxonomic approach reveals that the mystery is not random. There are patterns in the chaos. But the exceptions are what truly illuminate the path forward. The fact that rotational mysteries cut across all traditional categories suggests that our map of the galaxy zoo is incomplete. We have been sorting these cosmic creatures by their color and size, while ignoring the vital clue of how they move. Updating the Hubble sequence to include kinematic families, to create a classification that marries shape with motion, would be a revolution. It would be like biology adding DNA analysis to its study of species. This new taxonomy would not just describe what a galaxy looks like, but would tell the story of how it came to be. Some of the universe's most profound secrets hide in its faintest lights. Drifting through the dense Coma cluster, astronomers discovered a new class of cosmic phantom, the Ultra-Diffuse galaxy. These ghostly islands are as large as our own Milky Way, but they contain only 1% of its stars, spreading their faint glow so thin they had been almost invisible against the blackness of space. Finding them required a new kind of eye, an instrument like the Dragonfly telephoto array, which uses clusters of commercial camera lenses to suppress scattered light and reveal these vast, wispy structures. Their discovery was a shock. How could something so large contain so little? The mystery only deepened when astronomers turned their most sensitive spectrographs toward these dim giants, attempting to measure their spin. Kinematic studies of ultra-diffuse galaxies are a monumental challenge. Their light is so feeble that gathering enough photons to map their motion can require dozens of nights of observation on the world's largest telescopes. Yet the data that slowly emerged was worth the wait. Some of these UDGS, like the famous Dragonfly 44, displayed rotation that defied all logic. Dragonfly 44 has a total mass comparable to the Milky Way, a weight that suggests a powerful gravitational pull. But this mass is almost entirely composed of dark matter, with only a tiny sprinkling of visible stars. Its rotation speed is unexpectedly slow and strangely disordered, a faint whisper of motion that does not match the massive, invisible anchor holding it together. Other ultra-diffuse galaxies show hints of retrograde motion relative to the flow of their host cluster, spinning backwards against the cosmic current. Are these phantoms failed galaxies whose dark matter halos formed normally but for some reason never managed to condense enough gas to birth a full population of stars? Or are they the stripped and tattered remnants of once normal galaxies, shredded by their violent passage through a dense cluster? In the tidal stripping scenario, a spiral galaxy venturing too close to the cluster's core can have its stars and gas violently torn away, leaving behind a dark matter-dominated skeleton that retains only a faint echo of its original spin. The evidence is conflicting. Some ultra-diffuse galaxies show the telltale signs of this tidal violence, while others appear pristine and undisturbed, as if they were simply born this way, quiet and diffuse from the beginning. Researchers using deep imaging with the Hubble Space Telescope and spectroscopy from the Keck Observatory are piecing together the life stories of these ghosts. Each new observation seems to deepen the puzzle. One team found an ultra-diffuse galaxy with a surprisingly robust system of globular clusters, hinting at a rich and complex history that belies its faint appearance. Another study identified UDGS with internal rotations so bizarre they cannot be classified within our standard galactic models. These faintest of galaxies present the most severe test for our theories. Their strange rotation cannot be easily explained by our standard dark matter models or by modified gravity alone. They exist in a liminal space, challenging our very definition of what a galaxy is and how it should behave. The silent, slow spin of an ultra-diffuse galaxy is a profound reminder. The cosmos writes its most important lessons not only in the brilliant spirals, but in the faintest of whispers, urging us to listen more closely to the darkness. The brilliant stars and glowing gas clouds we see in a galaxy are not just passive passengers. This ordinary matter, what scientists call baryonic matter, holds its own surprising power to reshape a galaxy's destiny. While dark matter provides the gravitational framework, the constant cycle of stellar birth and death acts like a cosmic sculptor, chiseling away at a galaxy's rotation over billions of years. The most dramatic of these sculpting tools is stellar feedback. When massive stars reach the end of their short, violent lives, they explode as supernovae. These titanic blasts launch fierce winds of gas and radiation, hurling material outward at millions of miles per hour. This is not a gentle process, it is a galactic-scale eruption. Imagine a spinning office chair holding a person with outstretched arms. If that person suddenly throws a heavy weight in one direction, the chair will recoil and spin the other way. A supernova explosion does the same thing to a galaxy. By ejecting vast amounts of mass in one direction, it imparts a tiny recoil, a slight change in the galaxy's angular momentum. A single supernova is a negligible push, but when thousands or millions of them erupt across a galaxy over eons, their collective force can gradually torque the entire system, altering its spin axis or even contributing to a reversal. This is especially potent when star formation is lopsided. If one side of a galactic disk experiences a burst of new stars while the other remains quiet, the resulting supernova will fire like an uneven rocket thruster. The asymmetric feedback pushes harder on one side, slowly and persistently changing the galaxy's orientation in space. Supercomputer models that now include these complex baryonic physics reveal the stunning results. Galactic evolution expert Dr. Sarah Wellens notes that without feedback, our simulated galaxies are too massive and too regularly rotating. It is the messy, explosive input from stars that creates the diversity and the peculiar rotations we actually observe. In these digital universes, powerful outflows from supernova can sweep gas out of a galaxy's center, causing its inner core to slow down or even decouple from the outer disk, creating the kind of counter-rotating structures we find in real galaxies. We can even see this process in action. Astronomers point to galaxies with enormous bipolar outflows blasting from their cores, driven by either frantic star formation or a supermassive black hole. In several of these systems, the ejected gas is moving in a direction that contradicts the galaxy's primary rotation, a clear sign that internal forces are actively reshaping its angular momentum. Yet for all its power, stellar feedback is not a universal answer. The force of a million supernovae is still dwarfed by the immense gravitational grip of a dark matter halo. It can nudge, it can warp, and it can complicate, but it is unlikely to single-handedly reverse the spin of an entire galaxy the size of the Milky Way. The true power of baryonic physics lies in its partnership with the invisible. Feedback can make a galaxy more susceptible to the gravitational influences of a merger or the subtle torque of its dark matter scaffold. It is this intricate dance between the seen and the unseen, between the explosive fury of stars and the silent pull of darkness, that may ultimately choreograph the strange and backward spins across the cosmos. The very first moments of our universe might hold the ultimate key to this cosmic spin mystery. To understand why a galaxy spins backwards, we must rewind time to the fiery dawn of everything, a fraction of a second after the Big Bang. In that searing heat, the cosmos was not perfectly smooth. It was imprinted with minuscule ripples, tiny variations in density known as primordial fluctuations. These imperfections were the cosmic lottery tickets that would one day determine the fate of everything, from the smallest star to the largest galactic supercluster. They were the seeds from which all structure would grow. As the universe expanded and cooled, gravity began to pull harder on the slightly denser patches. These over-dense regions started to draw in more and more matter, becoming the gravitational wells where the first galaxies would eventually form. But this process was not a simple, straight collapse. The arrangement of these density seeds was crucial. Picture a vast, invisible cosmic web even in its infancy, with hills and valleys of gravitational potential. A proto-galaxy forming at the edge of one of these hills would feel a gravitational tug from all sides. The pull from a neighboring density peak, slightly off to the side, would exert a tidal force. This is the mechanism of tidal torquing. It works like two people spinning a merry-go-round by pulling on opposite sides at just the right angle. Their combined off-center pulls set the entire platform spinning. In the early universe, the uneven gravitational landscape did the same thing to collapsing clouds of dark matter and gas. It gave them their very first twist, their initial angular momentum. The direction of that initial spin was essentially a cosmic coin toss, determined by the random quantum arrangement of those primordial density fluctuations. The result was a universe where, from the very beginning, some galaxies were destined to spin forward and some backward. This primordial perspective is not just theoretical. We can see its evidence today in the cosmic microwave background, the ancient afterglow of the Big Bang. This faint microwave light is a snapshot of the universe when it was only 380,000 years old. Cosmologists meticulously study its subtle temperature variations, which map those original density ripples. By analyzing the patterns in this cosmic background radiation, they can trace how those initial conditions would have evolved, predicting the statistical distribution of galaxy spins we should see today. Supercomputer simulations that start with these precise initial conditions do, in fact, generate virtual universes with a mix of forward and backward spinning galaxies. Yet there is a persistent gap. The number of retrograde rotators these simulations produce often falls short of the strange abundance we observe in the real cosmos. The primordial coin seems to be weighted, landing on the wrong way spin just a little too often in certain parts of the sky. This suggests that the random quantum processes of the infant universe might have had a hidden bias, a slight preference for configurations that lead to retrograde motion. Connecting a specific galaxy's spin today directly back to its primordial origin is the monumental challenge. Billions of years of cosmic evolution, of mergers, accretions, and internal feedback have overwritten much of that initial signature. It is like trying to discern the first gentle push on a spinning top after it has been kicked, jostled, and battered for eons. The pristine signal from the beginning of time has been clouded by 13 billion years of history. This forces us to look even deeper beyond the hot Big Bang, to the mysterious epoch of cosmic inflation. This was a moment of unimaginably rapid expansion in the very first instant of the universe, when the quantum fluctuations of a microscopic realm were stretched to cosmic proportions, becoming the density seeds for everything to come. The ultimate answer to why some galaxies spin the wrong way may be written in the fundamental physics of that inflationary dawn, a code we are only now beginning to crack. Deep within the heart of many galaxies lies a monster, a supermassive black hole with an appetite for stars and gas. When this cosmic beast feeds, it can unleash some of the most powerful forces in the universe, blazing jets of energy that shoot into intergalactic space for thousands of light years. These jets are not random. They act like a cosmic gyroscope pointing directly along the spin axis of the black hole itself, a line that is typically perpendicular to the swirling accretion disk of hot matter falling into it. We expect this axis, this fundamental direction of the central engine, to be neatly aligned with the galaxy's own spin, but the cosmos delights in breaking our expectations. We find galaxies where these powerful jets fire out at a bizarre angle, completely misaligned with the galactic disk they call home. A stunning example is the nearby radio galaxy Centaurus A. From our vantage point, it presents a classic, dusty spiral disk, but cutting across it is a thick, warped lane of dark dust, a clear sign of a past trauma. And spewing forth from its core are immense radio jets, not aligned with the plane of the galaxy at all, but shooting out at a sharp, awkward angle. It is as if the galaxy's heart is spinning on a tilt, its rhythm out of sync with its body. How does such a profound misalignment occur? The most likely culprit is a violent galactic merger. When two galaxies collide, their central black holes eventually sink to the new core and can merge into a single, more massive black hole. During this chaotic process, the incoming black hole can deliver a powerful gravitational kick, throwing the merged black hole's spin axis off kilter. Alternatively, the black hole might be fed by gas clouds that fall in from random, chaotic directions over billions of years, a process called chaotic accretion. Each new stream of gas carries its own angular momentum, constantly tugging and twisting the black hole's spin axis until it no longer matches the galaxies. The consequences of this misalignment are not just cosmetic. Astrophysicists who model active galactic nuclei have found that these off-kilter jets can act like a giant handbrake on the galaxy. As the powerful jets plow through the surrounding galactic gas, they can exert a significant torque on the entire system. One researcher specializing in this feedback noted that the transfer of angular momentum from a misaligned jet to the host galaxy is a slow but persistent process, capable of altering the galaxy's rotation over cosmic time. This raises a fascinating possibility. Could a severely misaligned central engine over billions of years actually help to slow down or even reverse a galaxy's spin? The dynamics are incredibly complex, but the theoretical groundwork suggests it is possible. These misaligned systems may be prime candidates for hosting the kind of internal torques that lead to retrograde motion or warped disks. When we look at a galaxy like Centaurus A, we are not just looking at a static picture. We are witnessing an ongoing cosmic struggle, a battle of spins between a titanic black hole and its galactic home. This adds a dramatic new character to our mystery, suggesting that the engines at the very center of galaxies are not just passive inhabitants. They are active sculptors, capable of writing their own twisted stories into the fabric of galactic spin. Our perspective from Earth is a prison of angles and assumptions. Every galaxy we observe is frozen in a single frame from our unique viewpoint, and this simple fact creates a hall of mirrors that can trick our most sophisticated instruments. The Doppler shift technique, so brilliant at mapping motion, relies on a critical piece of information: the precise tilt of the galactic disk relative to our line of sight. If a galaxy is presented to us face-on like a giant sparkling pinwheel, its rotation is beautifully clear, the red and blue shifts neatly divided across its arms. But when a galaxy is seen edge-on, a thin sliver of light against the dark, we lose almost all information about its spin direction. We can see it is spinning, but we cannot tell if it is turning clockwise or counterclockwise from our perspective. It is like trying to judge the spin of a coin tossed into the air when you are looking directly at its edge. The motion becomes ambiguous. For galaxies that are not perfectly edge-on but still highly inclined, the ambiguity remains. Our mathematical models attempt to deproject the observed velocities, to reconstruct the true three-dimensional motion from the two-dimensional image we capture. This process is fraught with uncertainty. It requires assumptions about the galaxy's intrinsic shape, the exact angle of its pole, and the symmetry of its rotation. A small error in estimating the inclination angle can flip the inferred direction of spin, making a perfectly normal galaxy appear to be a retrograde rotator. Astronomers specializing in data reduction describe this as a persistent headache in kinematic studies. One researcher noted that for every 10 candidate wrong-way spinners they identify, detailed reanalysis might correct 5 or 6 of them, revealing them to be projection effects. This happened with several galaxies in early catalogs, where improved measurements from instruments like the Atacama Large Millimeter Array provided a clearer view and resolved the apparent anomaly. Advanced statistical methods are now employed to combat this. Large, homogeneous surveys like MOND observe thousands of galaxies, allowing scientists to average out these individual biases and look for robust statistical trends in spin directions across the universe. They use complex algorithms to model the most probable intrinsic motion based on the observed shape and velocity field. Yet, even after applying the most rigorous corrections, a significant population of backward-spinning galaxies stubbornly remains. These are the systems viewed from favorable angles, with clear, high-quality data that confirms their rotation is genuinely reversed. The very fact that these anomalies persist through such careful scrutiny makes them all the more compelling. They are not mere phantoms of a flawed perspective. This critical look at our own methods is a necessary dose of humility. It reminds us that the map is not the territory. Our understanding of cosmic motion is filtered through layers of interpretation and limitation. The galaxies that continue to spin the wrong way, even after we have accounted for our own observational biases, are pointing toward a truth that lies not in our instruments, but in the deeper workings of the cosmos itself. These cosmic questions are about to meet their match. A new generation of astronomical observatories, both in space and on the ground, is poised to transform our blurry snapshot of galactic evolution into a high-definition movie. The James Webb Space Telescope, with its golden mirror peering deep into the infrared, is already revealing the delicate structures of infant galaxies in the early universe. Its powerful spectrographs can dissect the light from these primordial spirals, measuring their rotation at a time when the cosmos was only a fraction of its current age. This allows us to ask a critical question: were backward-spinning galaxies more common when the universe was young, or is their strange motion a product of a long, violent history? As one project scientist for a Webb early release program stated, "We are finally seeing the initial conditions of spin, reading the opening chapters of a story that has been hidden for billions of years." Soon, it will be joined by the Nancy Grace Roman Space Telescope, a wide-field surveyor that will map the sky at a staggering pace. Roman will not study a few hundred galaxies in detail, but millions. This vast statistical census will reveal the true prevalence of retrograde rotation, showing us how these anomalies correlate with a galaxy's environment, mass, and shape on a scale we can barely comprehend. It will find the rarest specimens, the isolated wrong-way spinners that currently defy all explanation, giving us a robust sample to finally understand their origins. On the ground, the revolution is just as profound. The extremely large telescope being built in the high Chilean desert will combine the light from a mirror nearly the size of a blue whale to capture images sharper than those from the Hubble Space Telescope. Its suite of instruments will act as a cosmic MRI machine, mapping the internal motions of stars and gas in distant galaxies with breathtaking precision. It will be able to detect the subtle warps and counter-rotating streams within galaxies so far away they appear as mere smudges to our current telescopes. Meanwhile, the Square Kilometre Array, a network of radio antennas spanning 2 continents, will tune into the faint radio whispers of cold hydrogen gas. This neutral hydrogen traces the outermost, most sensitive regions of a galaxy, where the gravitational influences of dark matter and the torques from the cosmic web leave their clearest imprint. The SKA will not just take a picture, it will create a dynamic map of how gas flows into and around galaxies, revealing the ongoing processes that might be slowly reversing a galaxy's spin over eons. One lead astronomer for the project expressed that they are essentially building a time machine to watch galactic evolution in action, to see the forces that torque and twist galaxies as they happen. These tools will work in concert, creating a multi-wavelength portrait of galactic spin across cosmic time. They will test the predictions of dark matter models against those of modified gravity with unprecedented rigor, searching for the tiny, telltale signatures that distinguish one from the other. They will hunt for the faint optical glows and strange rotations of ultra-diffuse galaxies by the thousands, determining if they are failed systems or stripped relics. The rapid acceleration of our technological sight fuels a tangible optimism. For the first time, we are not just building better cameras to look at the cosmos. We are building instruments that will watch the universe in motion, tracking the grand, slow-motion ballet of galactic spin from its primordial beginnings to its present-day mysteries. The answers to why some galaxies spin the wrong way are no longer trapped in the distant past. They are waiting in the data streams of the very near future. The cosmic dance of wrong-way spins is not limited to grand spirals. Even the smallest galaxies, the faint dwarf satellites that orbit giants like our Milky Way, move in ways that defy our expectations. These cosmic minnows should follow predictable paths, orbiting in a placid disk around their host, much like planets around a star, yet many of them break this mold entirely. The most famous of these are the Magellanic Clouds, two irregular dwarf galaxies visible from the southern hemisphere. They are not orbiting within the flat plane of the Milky Way's disk. Instead, their path is steeply inclined, and studies suggest their motion might even be retrograde, carrying them backwards against the flow of our galaxy's own rotation. Another striking case is the Sagittarius dwarf spheroidal, a galaxy currently being torn apart and consumed by the Milky Way. Its debris forms a vast, looping stream of stars that wraps around our galaxy in a polar orbit, a path that is nearly perpendicular to everything else. For cosmologists, these peculiar orbits are a deep puzzle. The standard model of hierarchical structure formation, where large galaxies grow by consuming smaller ones, predicts that incoming dwarfs should be funneled in along the dark matter filaments of the cosmic web. This process should lead to orbits that are more or less aligned, not these wildly misaligned and retrograde paths. These small galaxies seem to have retained a stubborn memory of their initial conditions, a directional impulse from their first approach billions of years ago that the host galaxy's gravity has failed to erase. The gravitational interplay between a dwarf and its giant host is a violent one. Tidal forces stretch the smaller galaxy, stripping away its stars and gas to form long, shimmering tails. This relentless pulling can certainly alter a dwarf's rotation, stirring its internal motions into chaos, but the outcome is not always predictable. In some cases, the tidal interaction might randomize the spin, while in others, it could lock it into a new, unexpected configuration. The dark matter content of these dwarfs is another critical factor. Many are thought to be dominated by massive, dense dark matter halos, which could help them maintain their structural integrity and peculiar motions even as they are being dismembered. The sheer diversity of motions within our own local group of galaxies tells a compelling story. Some dwarfs orbit with the spin of the Milky Way, some against it, and some plunge straight over the galactic poles. This chaotic zoo of orbital behaviors underscores a profound truth. The mystery of backward motion is not a singular anomaly for giant galaxies alone. It is a universal phenomenon, a thread that connects the grandest spirals to the faintest dwarfs. This shared puzzle, spanning such a vast range of scales, points toward common underlying causes, forces that weave through the entire cosmos and touch every island of stars, no matter how large or small. A single type of data is like hearing one instrument in a grand orchestra. You might follow the melody, but you miss the harmony, the rhythm, and the full emotional power of the symphony. This is the fundamental limitation of traditional astronomy. For centuries, we have studied the cosmos almost exclusively through light, from the visible starlight collected by Galileo's telescope to the radio waves and gamma rays detected by our modern observatories. Each wavelength reveals a different piece of the galactic puzzle. Radio telescopes map the cold hydrogen gas that traces a galaxy's outermost skeleton. Infrared light pierces through obscuring dust to show where stars are truly forming. X-rays reveal the scorching gas halos heated by supernova explosions. Yet even this multi-wavelength view is still just one messenger, one way of listening to the cosmos. It is like trying to understand a complex machine by only looking at it, never touching it or hearing it run. The future lies in combining these electromagnetic observations with entirely new cosmic messengers. The revolutionary detection of gravitational waves has opened a completely different sense. Instruments like LIGO and Virgo do not see light. They feel the subtle ripples in spacetime itself, vibrations caused by the most violent events in the universe, like the merging of two black holes or neutron stars. While these collisions happen far from a galactic disk, they are profound signposts. Every merging black hole pair has a history, a story that began within a galaxy. The spin axes and orbital dynamics of these merging pairs carry an imprint of their birth environment. A population of black holes consistently merging with a certain spin orientation could, statistically, point toward the kinds of galactic interactions and mergers that produce retrograde rotation. It is an indirect clue, a whisper from the dark that complements the shout of the light. The most holistic strategy, known as multi-messenger astronomy, weaves together light, gravitational waves, and even elusive particles called neutrinos. As one director of a multi-messenger institute explains, we are no longer just astronomers. We are cosmic detectives assembling a case from every possible piece of evidence. A single anomaly, like a galaxy spinning the wrong way, can be studied with traditional telescopes to map its stars and gas. But if, by chance, a gravitational wave observatory also detects a merger from that same general region of the sky, the combined data could reveal if a recent collision is the culprit. Alternatively, a neutrino detector catching a burst of these ghostly particles from the galaxy's core could indicate intense activity around its central black hole, a potential engine for torquing its spin. We have already seen the breathtaking power of this approach. The landmark event in 2017, when a neutron star merger was detected simultaneously in gravitational waves and across the electromagnetic spectrum, transformed a theoretical model into an observed reality. It confirmed where heavy elements like gold are forged and provided a direct measurement of the universe's expansion. Applying this same integrated logic to the mystery of galactic spin is the next frontier. Imagine trying to solve a jigsaw puzzle, but the pieces are scattered across different boxes. One box holds the shape of the pieces, another their color, and a third their texture. Only by combining them all can you see the complete picture. For a backward-spinning galaxy, the optical data gives us its shape and velocity. The radio data maps its magnetic field and outer gas structure. Future gravitational wave statistics might tell us about its merger history. Bringing these disparate datasets together could reveal, for instance, that an isolated retrograde rotator has a powerful, ordered magnetic field and shows no signs of a past merger. This would point the investigation away from collisions and toward internal or primordial causes. While this specific application is still in its infancy, the potential to break the deadlock is immense. The true answer may not lie in a single flash of insight from one telescope, but in the quiet convergence of many different streams of cosmic evidence. Our most fundamental theories of gravity are being stretched to their breaking point by these galactic anomalies. To venture beyond them, we must step into the speculative frontiers of physics, where concepts like string theory and loop quantum gravity offer radical new possibilities. These frameworks suggest that the very fabric of spacetime might be more complex than Einstein envisioned, especially in the weak gravitational fields that dominate galactic outskirts. String theory, for instance, proposes that the universe is not made of point-like particles but of tiny, vibrating strings. The different vibrations of these strings give rise to all the forces and particles we see. Crucially, this theory requires extra dimensions of space, dimensions curled up so small we cannot perceive them. These hidden dimensions could introduce subtle new forces or modify gravity on galactic scales, perhaps creating the equivalent of wrinkles in spacetime that nudge a galaxy's spin in an unexpected direction. One theoretical physicist working on these ideas describes it as gravity leaking into other dimensions, a slow seepage that could alter how a galaxy holds itself together. Another leading framework, loop quantum gravity, pictures spacetime not as a smooth continuum, but as a network of finite loops, a kind of quantum foam. On the smallest scales, this foam would be a turbulent sea of fluctuations, while these quantum effects average out to produce the smooth spacetime we experience locally. On the vast scale of a galaxy, the cumulative effect of this underlying graininess might slightly tweak the laws of motion. It would be like trying to sail a ship across an ocean that appears perfectly flat, but is in fact made of countless tiny ripples. Over an immense voyage, those ripples could ever so slowly alter the ship's course. The hypothetical mechanisms are breathtaking. Perhaps a galaxy drifting through a region of spacetime with a particular quantum texture experiences a different effective gravity, one that could torque its disk over billions of years. Or maybe the dark matter halo itself interacts with this quantum foam in a way that transfers angular momentum, slowly reversing the spin of the visible stars within. The challenge, and the reason these ideas remain in the realm of theory, is that their effects are incredibly subtle. They are drowned out by the vastly stronger forces of conventional gravity and baryonic physics. Detecting the signature of extra dimensions or quantum spacetime would require precision measurements far beyond our current capabilities, perhaps involving the gravitational waves from black hole mergers in distant, anomalous galaxies. As one researcher candidly admits, we are searching for a needle in a cosmic haystack, and we are not entirely sure what the needle looks like. Yet the persistent mystery of the backward spinning galaxies provides a powerful motivation to keep looking. If proven, these theories would not just solve one cosmic puzzle. They would revolutionize our entire understanding of reality, revealing a universe woven from strings or loops instead of points and fields. They represent the ultimate promise that the most perplexing problems in astronomy often point toward the next great leap in fundamental physics, urging us to look deeper into the hidden architecture of the cosmos. Some galaxies refuse to follow any script at all. Their motion is not merely backwards, but a form of celestial anarchy. Kinematic maps of these systems reveal a stunning mess of velocities, a starburst of arrows pointing in every direction with no clear axis of rotation. They are neither prograde nor retrograde, but exist in a state of pure chaos. The irregular galaxy Zwicky 18 is a prime example. It appears as a chaotic splash of young blue stars and glowing gas, and its internal motions are just as disordered, with stars and gas clouds moving on random, intersecting paths as if the entire system is tumbling through space without a central pivot. Even more structured-seeming systems can hide this internal tumult. Polar ring galaxies feature a central disk of old stars spinning one way, encircled by a perpendicular ring of gas and stars orbiting in an entirely different plane. The components move independently, like two separate galaxies sharing the same space but ignoring each other's gravitational rules. This profound disorder points to a uniquely violent history. A recent head-on galactic merger could completely scramble the ordered rotation of the original systems, leaving behind a turbulent blend of stars with no collective spin. Alternatively, an epoch of incredibly intense stellar feedback with supernova erupting like a chain of bombs could have stirred the galactic pot into a froth, randomizing the motions of the remaining stars. Astronomers who specialize in these kinematic outliers describe them as the ultimate challenge to our classification schemes. One researcher noted that when you see a galaxy with no coherent rotation, it forces you to question the very definition of a galaxy. Is it simply a gravitationally bound collection of stars, or must it also possess a certain dynamical order? Our most sophisticated computer models struggle to recreate these no-pattern galaxies. The simulations tend to settle into stable, rotating disks over time, unless the initial conditions are tuned to an extreme level of violence or the feedback physics is cranked up to unrealistic levels. Their chaotic nature defies our neat dynamical categories, making them impossible to analyze with the same tools we use for orderly spirals. This raises a profound question. Are these chaotic galaxies the extreme, final expression of all the rotation anomalies we have discussed, or do they represent an entirely different phenomenon altogether? Perhaps they are not failed spirals, but successful examples of a rare galactic form, one that thrives on disorder. Their existence is a powerful reminder of the sheer diversity of cosmic structures. They underscore the limits of our current paradigms, showing that our models must become far more flexible to account for a universe that is not only stranger than we imagine, but stranger than we can imagine. Solving the universe's greatest puzzles is no longer a job for professionals alone. A new kind of astronomer has joined the hunt, one sitting at a kitchen table with a laptop and a cup of coffee. Across the globe, hundreds of thousands of volunteers are now scanning images of distant galaxies, their collective eyes forming a digital observatory of unprecedented scale. This is the world of citizen science, and it is revolutionizing our search for the galaxies that spin the wrong way. The most famous of these projects is Galaxy Zoo, a website that invites anyone with an internet connection to help classify galaxies. You are presented with a stunning, real image from a telescope survey and asked a simple question: is this galaxy a smooth ellipse or a spiral? And if it is a spiral, which way are its arms winding? This seemingly simple task is something computers still struggle with, but the human brain is exceptionally good at recognizing patterns. The collective power of these human classifiers is staggering. One of the project's founders noted that what would take a single researcher a lifetime to classify, the Galaxy Zoo community can accomplish in mere days. This global team of cosmic detectives has already made remarkable discoveries. Volunteers were the first to identify a whole new class of objects they nicknamed green pea galaxies, small, compact, and intensely greenish galaxies undergoing furious star formation. They have also spotted rare polar ring galaxies and countless strange, disturbed systems that computers had filtered out as noise. Every one of these oddities is a potential clue. A galaxy with a bizarre, twisted morphology spotted by a volunteer in Ohio might be the very system that holds the key to understanding how galactic spins get flipped. The process is a beautiful form of crowdsourcing. When multiple volunteers flag the same galaxy as peculiar, it rises to the top of a list for professional astronomers to investigate with powerful telescopes. It is like having a million assistants sifting through the cosmic haystack, pointing directly at the most promising needles. One participant, a retired teacher from Sweden, described the thrill of knowing she might be the first person in history to ever really look at a particular galaxy and notice something off about its structure. These large datasets from monumental surveys like the Sloan Digital Sky Survey are made public, turning the entire internet into a collaborative research lab. The value is not just in the number of eyes, but in their diversity. A graphic artist might notice a subtle symmetry a physicist overlooks. A school child might be drawn to a splash of color that signifies a rare event. This influx of fresh perspectives breaks down the tunnel vision that can sometimes limit specialized research. The director of a citizen science platform explained that they are not just classifying data, they are building a community that is personally invested in the outcome of these cosmic mysteries. This engagement does more than just accelerate discovery. It rebuilds the connection between humanity and the night sky, fostering a deep public interest in astronomy that inspires the next generation of scientists. While a volunteer clicking on images may not directly solve why a galaxy spins backwards, their collective effort enriches the entire field. It ensures that no strange galaxy goes unnoticed, and that every potential clue in the vast cosmic mystery is flagged for investigation. This collective endeavor proves that the quest to understand our universe is not confined to mountaintop observatories. It is a journey that belongs to everyone. These galactic anomalies are far more than a technical puzzle. They are a profound lesson in the nature of science itself. Every wrong-way spin is a quiet rebellion against our cherished models, a cosmic nudge reminding us that our understanding is always provisional. The history of astronomy is written in these moments of disruptive data. For centuries, the geocentric model placed Earth serenely at the center of everything, a comforting illusion shattered by the stubborn retrograde motion of planets like Mars. That apparent backward loop in the sky was not a flaw in the cosmos, but a flaw in our perception, a puzzle that only made sense once we dared to imagine a sun-centered system. The philosopher of science Karl Popper argued that scientific progress does not come from proving theories right, but from finding the crucial instances that prove them wrong. These backward-spinning galaxies are our modern version of the retrograde planet, a persistent anomaly that refuses to fit the mold. They force us to question the invisible dark matter we have postulated, the laws of gravity we hold sacred, and the very story we tell about how cosmic structures are born. What does it say about our quest for knowledge that the universe consistently presents us with phenomena that defy easy categorization? This journey is not a straight path toward a final answer, but a continuous cycle of mystery, challenge, and revision. It demands a deep and necessary humility. We are a species on a small planet, attempting to decipher the rules governing hundreds of billions of star systems, many of which operate in ways we cannot yet explain. The cosmologist Carl Sagan captured this sentiment perfectly when he reflected that the universe is not required to be in perfect harmony with human ambition. Our maps of the cosmos are brilliant achievements, yet they are still just maps, and every wrong-way galaxy is a territory that does not conform. This is not a failure of science, but its very engine. The discomfort of not knowing is what fuels the most brilliant innovations. Will we ever arrive at a complete theory, a final set of equations that explains every spin and warp? Or is the universe inherently layered, with mysteries nested within mysteries, ensuring that the act of questioning never ends? The value may not lie in a final destination, but in the expansion of our imagination that occurs along the way. Each galactic oddity is an invitation to look deeper, to think more creatively, and to embrace the beautiful, unsettling truth that there is always more to discover. Galaxies are supposed to be the steady metronomes of the cosmos, their rhythms set for billions of years. Yet astronomers are now gathering whispers of a far more volatile reality, one where a galaxy's very spin can appear to shift within a human lifetime. This is not a slow cosmic drift, but a rapid evolution that defies everything we know about galactic timescales. The concept seems impossible. A galaxy's rotation is governed by its immense angular momentum, a property so fundamental that it should be virtually unchangeable over anything less than an eon. To witness a measurable shift in a rotation curve over mere decades would be like watching a mountain range decide to stroll across the continent. The key to this mystery lies in a new field called time-domain astrophysics, where scientists treat the sky not as a static picture but as a dynamic movie. By taking precise, repeated measurements of the same galaxies year after year, they hunt for the subtlest tremors in their motion. They are looking for changes in the kinematic alignment, a shift in the axis of spin, or a warp that seems to be propagating through the disk at an unbelievable speed. One hypothetical trigger could be a sudden accretion event. Imagine a massive, invisible cloud of cold gas, a leftover filament from the cosmic web, finally falling into a galaxy's gravitational embrace. This incoming torrent of material would carry its own angular momentum, and as it splashes down onto the galactic disk, it could act like a hand slapping a spinning top, imparting a new twist and altering its rotation in a relatively short burst. Alternatively, the violent awakening of a supermassive black hole at the galaxy's core could be the culprit. As it begins to feed voraciously, the resulting energy output and powerful jets could exert enough radiation pressure on the surrounding gas to effectively push against the galaxy's rotation, applying a braking force or even causing a precession that changes its orientation. The technological challenge in spotting this is monumental. It requires instruments of phenomenal stability and precision, capable of detecting velocity changes that might amount to just a few kilometers per second across millions of light years. Early claims of such detections have often been attributed to measurement artifacts, the inevitable noise that comes from trying to observe such distant, faint systems. As one astronomer specializing in this painstaking work admits, distinguishing a true kinematic shift from an instrumental glitch is the greatest hurdle we face. They must rule out every possible source of error, from atmospheric distortion affecting ground-based telescopes to subtle calibration drifts in space observatories. So far, no case of rapid rotation change is considered universally confirmed. The evidence remains tantalizingly circumstantial, confined to a handful of active galaxies where the data from one decade seems to tell a slightly different story than the data from the next. But if even one of these cases were proven true, the implications would be staggering. It would mean that our models of galactic stability are profoundly incomplete. We have always assumed that a galaxy, once formed, settles into a long, predictable middle age. The possibility of rapid internal evolution suggests a far more turbulent and reactive existence, where a galaxy's fundamental dynamics can be rewritten by a sudden cosmic event. This adds a volatile, almost living quality to these island universes. They are not just slowly turning clocks, but dynamic entities capable of changing their own rhythm in response to the hidden currents of the cosmos. The sheer scale of the data is now beyond any human capacity to process. We have mapped millions of galaxies, each a complex system of motion, and hidden within that ocean of numbers could be the subtle signature of a cosmic rule breaker. This is where a new kind of partner enters the search, one built on silicon and code. Artificial intelligence and machine learning are transforming galactic astronomy from a craft of individual study into a powerhouse of pattern recognition. Imagine an assistant that never sleeps, one that can scrutinize the kinematic maps of 10,000 galaxies in the time it takes to drink a cup of coffee, searching for the telltale swirl of retrograde motion or the chaotic velocity fields of a no-pattern galaxy. These algorithms are not just fast, they are deeply perceptive. Using techniques like neural networks, scientists first train these systems on vast libraries of simulated galaxies. They feed the computer millions of virtual universes, showing it what a clean rotation looks like, what a merger remnant should resemble, and crucially, what a backward spin appears as in the data. The neural network learns the fundamental language of galactic motion, internalizing the patterns so completely that it can then spot anomalies in real telescope data that a human eye might dismiss as noise. A data scientist at one major observatory described it as teaching a child to recognize animal shapes in the clouds, but on a cosmic scale and with infinite patience. The results are already groundbreaking. In one recent project, a machine learning algorithm sifting through data from the Hubble Space Telescope identified a population of faint, warped galaxies that had been consistently misclassified by earlier automated systems. These were not just oddities, they were a new morphological class, and their peculiar shapes were directly linked to strange kinematic properties, including misaligned spins. The AI corrected a systematic bias, revealing a hidden thread in the galactic tapestry. These tools excel at correlation, finding hidden connections that would take researchers years to uncover. An algorithm can cross-reference a galaxy's rotation speed, its shape, its chemical composition, and its environment all at once, asking if there is a statistical link between, say, a high iron content and a propensity for retrograde motion. It might discover that galaxies with powerful central magnetic fields are more likely to host counter-rotating cores, a clue that could unite magnetic and dynamical theories. This is not about replacing the astronomer's intuition, it is about augmenting it. The human mind provides the creative questions, the big theories, and the drive to understand the why. The machine provides the raw, unbiased power to sift through the evidence, pointing our attention to the most promising mysteries. One project lead put it succinctly, the AI is our guide through the data jungle, showing us the strange fruits we would have otherwise walked right past. It handles the immense burden of calculation, freeing us to do what we do best, which is to wonder, to interpret, and to tell the story of the cosmos. In the hunt for the ultimate cause of backward-spinning galaxies, this silicon partnership may be the key that finally unlocks the pattern hidden within the chaos. The universe in its youth was a place of chaos and creation, and the first galaxies were far from the orderly spirals we see today. We are now witnessing their turbulent infancy through the eyes of our most powerful time machines, telescopes like the James Webb Space Telescope and the Atacama Large Millimeter Array. These instruments peer back to a time just a few 100 million years after the Big Bang, capturing light that has traveled for over 13 billion years to reach us. In these deep field surveys, we find primordial galaxies ablaze with the fire of newborn stars, their shapes irregular and clumpy, but it is their motion that delivers the greatest shock. When astronomers point the sophisticated spectrographs of the JWST at a galaxy like JADESG S13, they measure a rotation curve that is completely flat. This galaxy, seen when the universe was a mere 600 million years old, already shows the gravitational signature of a strong, invisible hold, its outer gas racing just as fast as its inner stars. Other young galaxies, such as one observed by ALMA in the Hubble Ultra-Deep Field, display no coherent rotation at all. Their velocity maps are a scrambled mess, with different gas clouds moving in opposing directions, as if the entire system is still struggling to decide which way to spin. This primordial disorder directly challenges the idea of slow, graceful galactic maturation. We assumed that galaxies gradually settled into stable disks over billions of years. Instead, we are finding that some were born with mature dynamics, while others were born in a state of dynamical confusion that included retrograde motion. The conditions in the early universe were fundamentally different. These nascent galaxies were rich with gas, the raw fuel for star formation. A typical young galaxy might have a gas fraction of 50% or more, compared to the 10% found in a modern spiral like the Milky Way. This high gas content made them incredibly dynamic and volatile. When a massive cloud of gas collapses under its own gravity to form a galaxy, the ensuing burst of star formation is not a gentle process. It is a ferocious storm of supernova that can violently stir the surrounding gas, randomizing its motion and potentially setting the entire system spinning in an unexpected direction from the very start. Cosmologists studying these formation epochs express a shared surprise at the sheer diversity. One researcher analyzing JWST data noted that the early universe seems to have been experimenting with every possible type of rotation, as if testing the rules of galactic dynamics before settling on the more familiar patterns we see today. This raises a critical question: was wrong-way spinning actually more common in the past? The data is not yet conclusive, but the sheer number of disordered and anomalous rotators in the early cosmos suggests that retrograde motion might have been a standard feature of galactic youth, not a rare pathology. The implication is profound. The stately, ordered rotation of a galaxy like our own may not be the default state of the universe. It could be an achievement, a hard-won stability reached only after billions of years of coming from a violent and chaotic birth. These ancient galaxies are more than just distant smudges of light. They are fossil records of the universe's first attempts to build order from chaos, offering us the ultimate clue. The mystery of the backward-spinning galaxy may not be about what went wrong, but about how anything ever managed to spin right at all. The swirling patterns of a galaxy share a deep, hidden kinship with the turbulent flow of a river or the intricate dance of a flock of starlings. These are all complex systems, and their behavior often follows universal rules that transcend any single field of science. The same mathematics that describes the formation of a whirlpool in your kitchen sink can be applied to the birth of a spiral arm in a distant galaxy. This realization is breaking down the walls between scientific disciplines, creating a powerful fusion of ideas. Astrophysicists are now collaborating with experts in fluid dynamics, plasma physics, and even biology, asking a profound question. Could the mystery of the backward-spinning galaxy be solved not by a new telescope, but by a new equation borrowed from a completely different science? Fluid dynamicists have spent centuries studying turbulence and vortex formation. They understand how a spinning vortex can spontaneously split, creating counter-rotating flows within a single body of fluid. When they look at a galaxy like NGC 4550, with its two populations of stars moving in opposite directions, they do not just see a cosmic oddity. They see a familiar, if immensely scaled-up, example of vortex dynamics. The galaxy becomes a vast, slow-motion fluid of stars and gas, and its strange motions might be the natural outcome of instabilities and shear forces operating over billions of years. One researcher who moved from studying ocean currents to galactic flows remarked that the equations of motion are strikingly similar, only the scales of time and space are almost incomprehensibly different. This cross-pollination of ideas is yielding tangible results. Plasma physicists who specialize in the behavior of electrified gases have long modeled the intricate interplay between magnetic fields and ionized matter. Their sophisticated simulations are now being adapted to study the interstellar medium, the thin gas that fills the space between stars. These models show how galactic-scale magnetic fields, weak as they are, can act like a subtle guide rail, slowly channeling the flow of gas and over eons, exerting enough torque to warp a disk or alter its spin. The galaxy is treated not just as a gravitational system, but as a colossal electromagnetic engine. An astronomer working with a plasma physics team described the collaboration as learning a new language to read an old book, suddenly seeing paragraphs that were always there but previously indecipherable. Even concepts from biology are offering fresh perspectives. The coordinated motion of a school of fish or a murmuration of birds is a classic example of emergent behavior, where simple rules followed by individuals lead to complex, organized motion for the group. Some theorists are exploring whether the collective motion of stars within a galaxy could be understood through similar principles of self-organization. Perhaps the backward spin in a galaxy is not a single catastrophic event, but an emergent property arising from the local interactions of star clusters and dark matter clumps. It is a shift in thinking from a top-down command where gravity dictates all to a bottom-up process where large-scale patterns arise from countless small decisions. This approach reframes the galaxy as a living, evolving ecosystem rather than a static machine. The true power of this interdisciplinary approach lies in its ability to generate hypotheses that would never occur to a pure astronomer. A scientist studying weather patterns on Jupiter with its persistent great red spot and swirling cloud bands might see a gas giant as a laboratory for galactic-scale fluid dynamics. The same turbulent energy transfer that drives Jupiter's storms could be operating in the halos of galaxies, stirring the dark matter and influencing the spin of the visible disk. By looking beyond their own field, astronomers are assembling a new toolkit filled with analogies, models, and ways of thinking. The ultimate explanation for a retrograde galaxy may not be a single cause, but a symphony of forces, a complex dance of gravity, magnetism, and fluid motion governed by universal principles we are only beginning to comprehend. The key to the cosmos might have been hiding in plain sight, written in the language of other sciences all along. A telescope's mirror is polished with funds that could feed a city, and its data reveals secrets with no apparent use. This tension lies at the heart of our cosmic quest. When Earth grapples with poverty, conflict, and climate crises, can we ethically justify spending billions to decipher why a distant galaxy spins backwards? The question is not merely philosophical, it is a practical challenge faced by every scientist who applies for a grant and every politician who allocates public money. An astrophysicist might argue that knowledge is an inherent good, a vital part of what makes us human. A social ethicist would counter that our first duty is to the immediate suffering on our own planet. This is not a new debate, but the scale of modern big science makes it more acute than ever. The pursuit of abstract cosmic puzzles must constantly earn its place in the human enterprise. Yet history provides a powerful counterargument, one written into the technology we use every day. The development of the Global Positioning System, GPS, is a classic example. The satellites in orbit must account for subtle effects predicted by Einstein's theory of relativity, that time itself runs slightly faster in the weaker gravity of space. Without this correction, which emerged from a physicist's seemingly useless thought experiment about the universe's fundamental rules, your navigation app would guide you into a field within minutes. The lasers in our DVD players, the wireless internet in our homes, and the medical imaging in our hospitals all trace their origins to fundamental research that began with someone asking a beautiful, impractical question about the nature of light or matter. We never know which thread of curiosity will weave the fabric of our future. Exploring galactic spin requires pushing the limits of detector technology and computing power, innovations that inevitably ripple out into the wider economy. More profoundly, this kind of research is an investment in our intellectual capital. It trains a generation of problem solvers who can think in terms of complex systems and billion-year timescales, skills that are desperately needed to tackle the intricate, long-term problems we face on Earth. The director of a major observatory once noted that we are not just building telescopes, we are building minds. The value is not only in the answers we find, but in the new ways we learn to think. This endeavor also fulfills a deeper human need, one that is easy to dismiss but impossible to extinguish: the need for wonder. A child who sees an image of a warped galaxy from the James Webb Space Telescope is not just learning an astronomy fact. They are being invited into a story much larger than themselves, a narrative of mystery and exploration that can ignite a lifelong passion for learning. This sense of shared awe is a powerful social good. It reminds us that beneath all our terrestrial divisions, we are a single species living on a fragile rock, united under the same cosmic sky. It fosters a perspective that is both humbling and uplifting, a cosmic context for our human struggles. The philosopher and astronomer Carl Sagan expressed this beautifully when he wrote that astronomy is a humbling and character-building experience. There is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. To foreclose on this source of inspiration is to risk a spiritual and intellectual poverty. What is the moral imperative here? Is it not also an ethical act to nourish the human spirit, to fuel the imagination, and to ensure that our culture continues to look upward and outward? The very act of seeking to explain the galaxy's backward spin is a declaration that our curiosity and our capacity for awe are essential parts of our humanity. These discoveries hold the power to rewrite our cultural narratives. Learning that the universe is far more chaotic and wondrous than we assume challenges rigid worldviews and invites a more nuanced understanding of existence. It teaches us that the universe is not required to conform to our expectations, a lesson in humility that is deeply needed. The quest to understand a spinning galaxy is, therefore, not a diversion from our earthly responsibilities. It is part of the same continuous project to understand the world in all its complexity, from the climate of our planet to the rotation of an island of stars a billion light-years away. It is all one investigation, driven by the same insatiable human need to know where we are and why we are here. Our journey through this cosmic puzzle began with a simple, unsettling observation: a galaxy spinning in the wrong direction. We have traced this mystery from the first grainy photographic plates that hinted at retrograde motion to the razor-sharp data from our most powerful observatories, which confirmed these anomalies are real. We have explored the invisible hand of dark matter, the violent drama of galactic mergers, and the subtle, persistent torque of magnetic fields and cosmic environments. Yet for every elegant explanation, a serene, isolated galaxy spinning backwards quietly dismantles it. This is not a single mystery with a single solution, but a frontier where the fundamental forces of our universe collide. It is a puzzle that weaves together gravity, dark matter, baryonic physics, and perhaps the very fabric of spacetime. The enduring enigma of these wrong-way spinners perfectly exemplifies how science truly progresses. It is not a march of certainties, but a dynamic dance of questions. Every anomaly that refuses to fit our models is not a failure. It is an invitation to think more creatively, to collaborate across disciplines, and to build ever better tools to see the cosmos. This story is far from over. The next chapters will be written by the James Webb Space Telescope as it peers into the primordial dawn of spin, and by the colossal eye of the extremely large telescope as it maps galactic motion with unimaginable precision. These missions and the powerful new generation of radio arrays and citizen science projects are our best hope for turning this cosmic whisper into a clear answer. So stay curious, follow these discoveries as they unfold, and remember, each galaxy that spins against the tide is a profound message from the cosmos. It is a reminder that the universe operates on a scale of wonder and complexity that will always exceed our current grasp. Our greatest task is not to force the cosmos into our existing boxes, but to remain humble, open, and endlessly fascinated by the mysteries we have yet to solve.